it's on. Here's the mic.
Okay, so welcome to our first colloquium of the season, the first IFT colloquium. Today we are very happy to have with us Nima Arkani Hamed, who is a Severo Ochoa visiting professor with the IFT. And he has been also visiting very fast the previous workshop we just ended. So Nima needs no introduction, of course, for most of you, but just for the benefit of the young students, let me just say that he got the PhD for Berkeley sometime in the late 90s, I believe. Then he worked at SLAC, Harvard, and then moved to the Instituto of Advanced Study in Princeton, where he has been ever since. And during this time, he became a leading figure across the whole field of particle theory, with important contributions going from classic problems of particle physics, such as the way we think about the hierarchy problem, to more theoretical questions having to do with hidden mathematical structures that we keep discovering in the good old quantum field theories that we use to describe the world, some of which we heard a little bit in the previous talk. But just to finish, let me just say that also for the benefit of the young students, we all know that Nima is one of the greatest motivational speakers in our field. So if you are a PhD student who is depressed about your work, etc., what you can do is to walk into one of Nima's talk or just grab one in YouTube, and chances are that you will come out believing that you are lucky to be entering the field in the best possible historical moment.
It's true, it's true.
With these very high expectations for his talk, let's welcome Nima to the stage. Thank you.
Thank you, thank you. All right, well, that was a spectacular introduction. Thank you. We can just go home now, I think. Okay, so this workshop that I sadly did not get to attend enough of has been about this fascinating topic of the distinction between the landscape of all possible solutions that people have found in consistent theories of quantum gravity and string theory in particular, and so-called Swampland, theories that appear like they might naively be consistent, but might have some hidden strange inconsistency with deep principles that we still don't know. But the entire subject, the whole discussion, might sound, if you're sort of far enough away, it might sound like a sort of a bizarre obsession, like a sort of an attempt to get a consolation out of a truly terrible thing that happened to fundamental physics, or certainly to a string theorists in the early 2000s, where they realized that, in fact, string theory was not going to uniquely predict the properties of the world around us. And there was this idea and the whole paradigm of a certain kind of unification, and the phrase theory of everything, and we'll predict the ratio of the mass of the electron, or the ratio of the mass of the electron to the mass of the muon, and all these things will come out of solving string theory. That was a continuation of a sort of a paradigm of the way high energy physics was going in the 1970s into the early 1980s. Those words, again, if you're far enough from the subject, theory of everything, predict all the coupling, infinitely many predictions, all that stuff, that was one set of words, and then all of a sudden something switched, and now no one is talking about that anymore, apparently. That's just gone, and now, first of all, it appears the majority of the people who work on the subject don't even talk about the world around us anymore, period. And if they do talk about the world around, they talk about all kinds of toy models, this world, that world, but not our world. And those that do talk about our world now have discussions about swamplands and landscapes and so on. So what the hell happened? Okay, so the purpose of this colloquium is really to put what the hell happened in some context, and to talk about how those of us who care about unification, and we all care about unification at a deep level, what's going on, and what the current status of this picture of unification that we all have in the back of our mind is, at least from my personal point of view. Okay, so that's how this talk connects with the subject of the workshop that just happened here. And I don't need to remind this mostly sophisticated audience that unification has been the driving theme of fundamental physics for 400 years. Ever since Newton realized that the same force that pulls the apple to the Earth keeps the moon going around the Earth, and then we understood that these phenomena that the ancients noticed, like lightning bolts and funny magnetic materials that push and pull, that these are all different aspects of the same thing. And then in the 20th century, we learned even deeper things. We learned that space and time are different aspects of the same thing. And we learned that we learned something even more radical. The world isn't deterministic. It's governed by the laws of quantum mechanics. And that had as one of its many consequences that particles and waves are, in some sense, the same thing. Really, fundamentally, there are particles, but they're not classical particles. And sometimes macroscopic collections of particles behaving quantum mechanically look like classical waves. And sometimes they look like classical particles. But there's fundamentally underlying quantum mechanical particles. And in all of these pictures of unification, first, seemingly disparate phenomenon were unified, and secondly, other phenomena that didn't seem to have anything to do with those two found a common explanation as well. For example, like electricity and magnetism are aspects of the same thing, and then light is an electromagnetic wave. There's a third thing that seemed to have nothing to do with the first two, which came along for the ride. Now, the principles that we learned in the 20th century are allow the following slogan, and this to me is my favorite slogan about what we learned in the 20th century. So there are these grand principles of relativity and quantum mechanics, and what we learned is that these two ideas, the unification of space and time in quantum mechanics, any one of these ideas taken in isolation puts some restriction on what physics can look like, but taken together, they put a shockingly constraining straitjacket on our imagination. In other words, if you lock up a bunch of theoretical physicists in a room and hand them the basic laws of special relativity and quantum mechanics and say, go, build universes that are compatible with both of these principles, well, if they were me, I would look at it for a little while and say, no, sorry, I can't do it. Can't be done. Okay? Then you need sufficiently competent theoretical physicists to realize that it can be done, but in incredibly constrained theories. And just so you have a rough idea why this is, it's because relativity tells you space and time are not so different from each other. Okay, the time can be mixed into space, and vice versa. Quantum mechanics changed everything about the world. It's not deterministic and so on, but time still plays a primary role. You're supposed to specify the state of a system at one time and evolves to another time. So relativity changed everything about the kinematics of space and time, but the world is still deterministic. Quantum mechanics changed everything about what physics is supposed to be about, but time is primary. And they don't speak naively the same language even. Even the kinematics is not the same. So you have to do a lot of work to make them fit together. And that work means that if you put these sufficiently competent theoretical physicists in a room, they would discover that theories that are compatible with both relativity and quantum mechanics, there's a very tiny set of possibilities for what they could be. So, for instance, all the interactions that we know of in nature are ultimately incredibly simple things. So all of electromagnetism is associated with this interaction with two electrons and a photon meet at a point in space-time. And if you take that basic interaction and concatenate it many, 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 many times, then that gives us all possible electromagnetic interactions. But fundamentally, there's this very simple thing that determines everything. Similarly, for gravity and the other interactions that we know of, the strong interactions and the weak interactions. And in fact, everything that we know of, all the elementary particles and their interactions, when we go to high enough energies where we can sort of ignore the masses of the particles, so some first approximation, we imagine everything is massless. We imagine in that regime, what do we have out there? Well, there's this very small menu of these little stick figure interactions with three things coming together at a point in space-time. Electrons and photons, we talked about electrons and gravitons, everything in gravitons, quarks and gluons, electrons, neutrinos, and W particles, with a very specific pattern of interactions that just essentially governs what precisely who can talk to who and what the strengths of the interactions are as free parameters. And concatenating these interactions over and over and over again generates everything that we know about the structure of the elementary particles and the forces that govern them today. So now, and the statement that relativity in quantum mechanics makes the structure of the universe inevitable is contained really in the following sort of theorem. This is essentially a mathematical theorem. It comes from physics, but it starts from some physical requirements that you can turn into some sharply posed problem, and you can solve the problem. And here's the statement that whatever the ultimate theory is, whatever the ultimate laws are, relativity in quantum mechanics guarantees that at long enough distances, no matter what's going on at very short distance, long enough distances, you're guaranteed to see, first, the dominant interactions are going to be the ones with elementary particles interacting with three things coming together at a point in space-time. That's interesting, not 12 things coming together at a point, just the simplest possible interaction, which is three things coming together at a point in space-time. And secondly, that the only spins that the particles are allowed to have can come from this little menu. Spin 0, a half, 1, 3 halves, and 2. That's it. The spin 2 guy is unique. You can only have one of them, and it causes massive particles to go around in orbits and so on. It's gravity, but you don't need to be Einstein. You don't need to think about falling elevators. You don't need to think about any of that stuff. Just ordinary special relativity and quantum mechanics completely dictates the properties of massless spin 2 particles and forces it to be general relativity at long enough distances. Okay? Similarly, all these other things, you can have any number of these guys, any number of these guys. The spin 1 guys have to have a special structure associated with them. The spin 3 you can have at most 8 of them. The spin 2 has got to be unique, and so on. But this is the answer to a problem. What theories of massless particles are compatible with relativity in quantum mechanics? And amazingly, this is the tiny list of possibilities. And I want to say already at this point, before we talk about whether forces come together and there's a beautiful structure that unifies everything, this is at a much deeper and more profound level a unification of a sort that no one would have dreamed about 50 years ago, 60 years ago. Okay? This means that we're talking about everything in nature in a common language. It's not like gravity is different than the weak interactions, is different than electrodynamics. There's a uniform picture, which is the consequence of the fusion of relativity and quantum mechanics that governs everything with exactly the same basic language and basic structure. Okay? So to me, this is a truly profound kind of unification. And what we're talking about after this, some of the things, in a sense, are less profound kinds of unification. There are more technical sorts of unification. The more interesting things that have been going on over the past 10 or 20 years are about more profound notions of this unification, even beyond what I'm telling you about. So that's really what the rest of the talk is about, is sort of going through the different ways that we've understood what the notion of unification could mean and where it's taking us. But already where we are now has given us this profound common language and structure that governs everything, and it's a consequence of gluing together of putting together special relativity and quantum mechanics. In fact, there's only one footnote to this story. The footnote to the story is what I told you governs massless particles. Okay, so the interactions of massless particles are ridiculously strongly constrained to come from that tiny menu. Now, you might think if you know what the massless particles are doing, the mass is a little detail on top of that. After all, when you go to incredibly high energies, you should be able to ignore the masses of the particles, just kinematically. And that's true by pure kinematics, but it's not true for a very important reason that we can get by counting on our fingers when we have particles with spin. You see, let's say we have a spin 1 particle, like the W particle. If it's massive, it has 3 spin degrees of freedom. That's because no matter how it's moving, you can go to a frame where it's at rest, and then by rotating your head, however it's spinning, you can see it spinning in 3 directions. So it has 3 spin degrees of freedom. But a massless spin 1 particle has 2 spin degrees of freedom, 2 polarizations. And it's because we can't catch up with it to tilt our head and see that it can spin in any direction you like. This little difference between 2 and 3, and if we did spin 2 particles, it would be the difference between 2 and 5. Massive spin 2 particles have 5 degrees of freedom, massless has 2. This difference is the heart of much of the drama of the last 50 or 60 years in theoretical physics, because it means that you can't just add mass as a little correction. There's extra degrees of freedom when particles have mass. So if you have a collection of massive particles with spin, as you go to very high energies, they should fall apart into their different helicity components, but there's a big constraint on the spectrum of massive particles you have. At low energies, the degrees of freedom they contain have to reassemble into one of these legal things that were allowed from the menu that I told you about at very high energies. And if you just did that in the standard model before July 4th, 2012, there would be a problem. There were not enough degrees of freedom in all the massive particles we know about, especially the W and Z particles associated with the weak interactions. They simply did not have enough degrees of freedom to reassemble into consistently interacting massless particles at high energies. And that's the story of the Higgs. The entire story of the Higgs particle is that you had to have something else, and a single one stinking extra particle was all that was needed in order to now smoothly allow to take the massive objects at low energies and have them reassemble into consistently interacting massless particles at very high energies. Okay? That's why the Higgs was so important. And in fact, that's what's so special about the Higgs, is that before we discovered the Higgs, of this menu of allowed things that nature could do compatible with grand principles, we had seen it use particles spin 1/2, 1 and 2. We had not seen it use elementary particles of spin 0, and we have still not seen it use elementary particles of spin 3/2. But it's remarkable that Higgs, the first elementary particle of spin 0 that we've seen, and it does a job. Okay? It does a job to finally allow us to consistently extrapolate all the physics we know at very low energies into something sensible that fits into this constrained world at very high energies. So the spin 3/2 is the last thing that we haven't seen, and the only way the spin 3/2 particles can exist is if nature has this famous symmetry of supersymmetry. So this is the dominant reason why theorists have liked supersymmetry for 40 or 50 years, is it's the last thing nature can do compatible with its general principles that we have not yet seen it do. And the story of the discovery of the Higgs is actually an example of nature using an opportunity. It's possible for it to have these particles, we just hadn't seen it use it, and it solves the problem. So it's worth continuing to look for supersymmetry for this reason alone, apart from a number of others. All right, so that's the summary of the 20th century principles, and as I say, to me, the main take-home message is that there is this incredibly constrained common language and framework for talking about everything. Even though they appear drastically different at long distances, when we go to very high energies, very short distances, there's this fundamental unity between all the interactions of these elementary particles. So, what are the central dramas of the 21st century now? And I think given the incredible constraints that we have on our thinking from space-time and quantum mechanics, it's especially startling that we have indications that both of these ideas are probably suspect. Now, I think you have to ask questions that involve gravity and cosmology in order to start seeing them, seeing these difficulties. But it's very likely that space-time is an approximate concept, and this is just because of quantum mechanics and gravity. And it's even possible that there are going to be limitations to quantum mechanics because of relatively esoteric questions in cosmology, but still important ones that I will come to later in the talk. I want to stress here that I don't mean that quantum mechanics is wrong or that any one of these stupid modifications of quantum mechanics that people, somehow this field exists where people think this is interesting to work on. I think there's absolutely nothing interesting going on in the subject called the foundations of quantum mechanics, blah, blah, blah. Zero. Okay, multiply the papers by 0 and nothing would change as far as importance of anything in the world. But what I'm saying here is that there are questions which quantum mechanics doesn't tell you how to answer. We'll talk about why, but there are questions where quantum mechanics begins to cry uncle when you start talking about making precise observations, especially in accelerating universes. And it's these questions where it could be that there's some indication for limitations of quantum mechanics, maybe a need for extending quantum mechanics to allow us to talk about things in situations where quantum mechanics doesn't give us a language yet. It doesn't give us things to talk about. By the way, I've had no sleep in a long time, so my internal sensor is really at nothing. So you might get a lot of those comments in the rest of this talk today. So sorry about that. It's something interesting in some of those papers, I'm sure. I'm positive. I may even have seen it once, although I can't remember. Okay. And we have another set of mysteries that has to do with the question of why we have a macroscopic universe, even though there are very violent quantum fluctuations as we go to shorter and shorter distances, higher and higher energies. So let me talk about some of these problems qualitatively in turn. So first, the Doom of SpaceTime. Here are the very simple thought experiments. You try to look at a little region of space and time. The uncertainty principle says that to see what's going on in a tiny region, you need a more and more powerful microscope, higher and higher energies to probe shorter and shorter distances. But at some point, you put so much energy into such a tiny region of space, E equals mc squared, so that region has an enormous amount of mass, and you collapse the region that you're trying to look at into a black hole, and so there's no way to get information out from the region that you're trying to look at. So the very act of trying to probe space and time at very, very short distances produces an object that makes it impossible to probe what's going on in the region you're trying to look at. So this happens at the famous Planck length, around 10 to the minus 33 centimeters, and it means there's no operational meaning to distances or times that are smaller than this famous Planck scale, 10 to the minus 33 centimeters, 10 to the minus 43 seconds. All right, that's the very simple thought experiment with the Doom of SpaceTime. Now the question, why is the universe big? Again, we have more and more, quantum mechanical fluctuations in a particle in a box mode in a box of some size. The quantum fluctuations are given by the wavelength that fits in the box. As you make, then if you just look at the half h bar omega from the harmonic oscillator, well, that omega is set by that length. As you make the box smaller and smaller, the length gets shorter and shorter, the frequency gets higher and higher, so there's more and more vacuum energy in a smaller and smaller box. And if you make just an estimate for the vacuum energy density, the energy over volume, if I shrink the size of the box, not past the point space-time breaks down, but somewhere in its neighborhood, I get a Planck energy over a Planck volume, and you don't need to do any calculations to know that this is disastrously unlike our universe, because that energy density would lead to curvature in space and time. The only word in this whole slide is Planck, which is Planckian. So either the universe would be curled up in a tiny size of order 10 to the minus 33 centimeters, it would be explosively doubling in size every 10 to the minus 43 seconds. Neither one of these things look anything like our world. So this is the character of good questions in fundamental physics. The questions are very simple to state. They're not esoteric, weird questions. We have very simple thought experiments say the notion of space-time breaks down. We have good indications that that very simple estimates about energy density in the vacuum is just wild off from what we see in the universe. So those are some of the dramas that we have to deal with. Now I want to talk about these questions in the context of this sort of general program of unification. And so what I want to do is spend the rest of the talk talking about a variety of notions of unification. First, I will talk about what you can call the Ming-Vase picture of unification. And this is the one that, if you grew up in the 1980s or 70s, reading Scientific American articles or watching Nova specials, that's the kind of picture of unification that people had in mind. That we have all these shards, we have these interactions, they look different from each other, but it's like a big jigsaw puzzle. And then we learn they're glued together into a more magnificent whole. And some kind of symmetry breaking broke them apart so that all we see now are the pieces lying around. We have to figure out how to put the Ming vase back together, okay? That's the 1970s notion of unification. In a sense, it's a notion of unification that's there in the standard model of particle physics with the breaking of electroweak symmetry. It's a notion that goes further into grand unified theory and which I think colored the thinking of a lot of particle physicists and high-energy physicists working on string theory in the 80s. The theory of everything picture, okay, is kind of this Ming vase, that there's this one underlying object and then all these things are going to fit fit into it. But in this more or less boring way, right? That you take this piece and you glue it to that one, and that one, they're just broke apart into pieces, and we just have to figure out how to glue them back together. All right, then, so I will talk about that. But then there's other kinds of unification. Perhaps a qualitative, very important qualitative point I want to stress, which we don't stress enough, is that there's something deeply wrong with this Ming Vase picture, and even more besides. This entire reductionist paradigm, the whole paradigm that the most fundamental laws are revealed at arbitrarily short distances, a paradigm that has stood us to very good stead for 2,000 years. If we understand anything about these even qualitative deep facts about quantum mechanics and gravity, and we know many more sophisticated things besides now, we know on very general grounds this reductionist dream is false. Okay? It is just not true that the fundamental laws are given at arbitrarily short distances. And as we'll describe, in fact, arbitrarily short distances don't exist. You see, the Doom of SpaceTime already suggests there's something wrong with this idea, because you can't even go to arbitrarily short distances. There are other indications that very, very high energies, instead of probing very short distances for gravitational reasons, starts probing very long distances again. Okay, so so the whole reductionist paradigm is fundamentally flawed, even if it's been very useful and a very useful guide so far. And because of gravity and quantum mechanics, we have lots of indications that there's some kind of correlation between the physics of very high energies and very long distances again. Not the usual expectation of it's very high energies and very, very short distances. All right. Then there's the topic that's been probably the dominant theme of thinking about most people in most theorists in fundamental physics for the past 20 years, is this amazing sort of unification between gauge theory and gravity. This equivalence, again, not like the Ming Vase where you're supposed to put them together, like this piece is gauge, this piece is gravity, and together they glue into a big super object, but that they're actually different aspects of the same thing. They're different equivalent descriptions of the same underlying system. So this is an even more profound kind of unification. And I think so. And it's been I think up to this point there are things that are either established or have enormous amounts of evidence going for them. And towards the end of the talk, I will talk about somewhat more speculative sorts of unification. Something I personally very strongly believe is that we will come to see that space-time and quantum mechanics are actually unified things. By which I mean that the picture that we got in the 20th century, that there's space-time, there's quantum mechanics, somehow we have to put them together, we have the straitjacket, quantum field theory lets us talk about both at the same time and so on, that we'll eventually see that in a deeper picture, that it's inevitable that there's both space-time and quantum mechanics. One can't exist without the other, and the correct way of thinking about the deeper way of thinking about things will show that space-time and quantum mechanics are sort of joined at the hip, and they have to emerge together from some more primitive building blocks. And there's starting to be some evidence, a little bit of evidence, circumstantial evidence, but I'll tell you some evidence for that point of view. So this is a unification between space-time and quantum mechanics. The most speculative thing I'll maybe spend 30 seconds on at the end is a unification between a system and an observer. And by the time you get that, by the time we get there, if we get there, you know what I mean. I will probably not have any time to talk about prospects for clues from experiment, but there are some slides there. And if by some miracle we get there, I'll say a little bit about what we might learn from experiment, about at least a small subset of some of these questions. All right, so let's first talk about Ming Vase unification. Okay. So let's go back to that menu that we had of particles in the standard model. And the Ming Vase picture of the world is that, yes, indeed, these look like they're different, they're strong, weak, and electromagnetic interactions, different sort of complicated, somewhat random spectrum looking spectrum of particles. But amazingly, this collection actually glues together if you imagine that the strong weak electromagnetic interactions came from the breaking of a larger unified symmetry like SU5, first, it fits into SU5. Secondly, this complicated collection actually glues into something much simpler. And if SU5 is further extended to SO10, and just adding one dinky particle, all these states, where there are 15 of them, plus the one dinky one that you add, is 16, and this is a single object, a single so-called representation of this larger symmetry, SO10. All right, and the remarkable thing here is that in this picture, there would be a coupling strength for 3, 2, and 1, but underlying at very high energies where they're unified, you would predict that there is a single coupling that relates all of them. So there are two miracles here. One is that this complicated spectrum actually seems to descend from something very simple like this. But two, something more quantitative, that the three apparently different coupling strengths should all be determined by one underlying one. Okay? So that's one remarkable picture, and it really began, I think, this whole paradigm that we are sitting here at very low energies, even though it's very high energies as far as particles or as far as experimentalists are concerned. But compared to very high energy scales like the Planck scale, we're sitting there at low energies. There's some kind of big desert between us and very, very high energies, and something unified is happening at super duper high energies, maybe somewhere near the Planck scale, or here it was the grand unification scale. Now, and in a sense, string theory was a natural continuation of that kind of a paradigm, even though it made a bigger change to the rules. So string theory says that no, indeed, we don't have point particles, we have little loops of string. The loops of string are around 10 to the minus 31 centimeters big in the standard picture. Note that 10 to the minus 31 centimeters, a little bigger than, about 100 times bigger than 10 to the minus 33 centimeters, which is the Planck length. That factor of 100 is around the fine structure constant. So the strings are actually somewhat bigger than the Planck length. But whereas for ordinary particles, we have interactions that look like this, with some which are first singular and secondly have some arbitrary interaction strength. In strings instead, we get to draw smooth pictures like this, and since there's none of these pinching places, there are no adjustable parameters that we could talk about here. And string theorists were very excited that gravity was somehow an inevitable part of this promotion of point particles, the little loops of string. So this is another indication. So this is quite striking and a very deep indication for unification. Not just, oops, I don't know what happened to my slide there. This was supposed to be a slide of this beautiful picture of the unification of the forces in supersymmetric theories. And if you draw, there's a straight line for the inverse of the coupling constants as we run them to very high energies. And they meet together at a point at around 10 to the 16 gigaelectron volts. Again, an energy scale around 100 or 1,000 times lower than the Planck scale, but within a factor of around 10 or so of the string scale. So first, quantitatively, there's this remarkable convergence of three different coupling constants to a unified value when we make the theory in between supersymmetric. And secondly, that unification is taking place at a scale that's first close to where gravity becomes important, but even in more detail, close to what should set the size of the strings. So this whole collection of ideas, grand unification, strings, the desert, supersymmetry, they all go together very beautifully. The particles group together in multiplets in this remarkable way. These couplings meet to percent accuracy at very high energies. All of this was the reason why when I entered graduate school, there was this strong sense that this was what was going to happen when we had turned on the LHC. We're going to have billions of gluinos to study, and that the job of my generation was to sort of clean up all the details and figure out how supersymmetry was broken. But people more or less knew the answer. And that was definitely people's sense, is that this is there's so many things that are obviously correct, and we haven't seen it. Okay? So what the hell is going on? This is a subject of a colloquium all by itself, and I've given several talks with the subject, with the title something like "What the hell is going on?" But I want to say that at least for myself, my own best bet for quite a long time has been, since around a little over 10 years ago, is that there is a picture of the world where all these experimental and theoretical clues that we've had for the past 30 years are not wasted. That's the tension the whole time has been the positive hints for something like supersymmetry and unification that I just told you. And also the whole time is a couple of negative hints. One is that if all these particles were lying around right above our head, we could have seen them already before. We could have seen them indirectly before. We could have seen them directly in accelerators long before the LHC. And so a number of people in the late 1990s were already saying there's something a little bit wrong with the fact that we haven't seen all these particles yet. We could have seen them already, okay, without luck. In fact, we should have seen them already. It was never clear how big a problem this was. And so people mostly didn't worry about it. It was a niggling problem, a little nagging issue. There was an elephant in the room the whole time, which is that at least some of the arguments that supersymmetry should show up right above our head at the energy scales probed by the LHC. The analogous arguments would fail drastically for the cosmological constant. So the reason we expected supersymmetry at the LHC was that supersymmetry controls violent quantum mechanical fluctuations associated with the Higgs, but we have even more violent quantum mechanical fluctuations associated with the vacuum, which is what I even talked about here, and we haven't, and yet there's no new physics associated with that. So that problem with the cosmological constant has been the elephant in the room the whole time. So there's a big elephant in the room. There are all these nagging reasons to worry that something was off with this standard picture. And yet, why did most people not worry about it? They said, look, whatever's going on, these are sort of vague, sort of maybe philosophical problems. But look, these concrete successes tell us that this must be right. And at least for me and some of my friends over 10 years ago, a picture emerged that allowed you to make sense of both of these things. And that was an unusual picture of supersymmetry, where supersymmetry does not solve some of the problems that we normally think that it solves. It's lying around for other reasons, but the scalars of supersymmetry are much heavier than the fermions. And just making the scalars a factor of around the fine structure, the universe fine structure constant, 100 times, 1,000 times heavier than the fermions. First of all, this is something which reasonably happens in theories that break supersymmetry. You have to actually do a little bit more work to guarantee that the scalars and fermions are roughly at the same scale. But secondly, if you do this and you make the scalars much heavier than the fermions, then many of these indirect niggling problems with supersymmetry disappear, but you don't affect that beautiful unification of the coupling constants, nor the fact that supersymmetry might provide you a natural candidate for dark matter. So the concrete successes are preserved. You get rid of these problems, but the Higgs was supposed to be one of these scalars of supersymmetry. So the fact that the Higgs is not sitting there at hundreds of TeV means that there has to be something weird going on, which supersymmetry was supposed to solve this problem. So that was the sort of heresy of this idea, is that we say the world is supersymmetric, but it has something that looks like a fine-tuning in it, something strange, so that the Higgs is not up where it should belong with the rest of the scalar particles. And of course, supersymmetry also doesn't tell you why the vacuum energy is as small as it is. So compared to that sin, this is a minor one. But this is a picture of the world where if you say for some reason there is something else out there which is dealing with this very large problem of the vacuum energy, it might, as an ancillary smaller thing, deal with the problem associated with the Higgs mass. And if it does that, then we can understand both why we haven't seen the superpartners yet, as well as why nonetheless things like unification worked and supersymmetry gave us a nice candidate for dark matter and so on. So anyway, I don't want to go through some of the other hints that there's something good about this idea. I will say that this picture did make a pretty loose prediction for the mass of the Higgs particle. to be somewhere between 120 and 135 GeV. And so the fact that it was discovered around 125 GeV means this theory is not dead. Okay, and it's not that may not sound like that might not sound like a ringing endorsement, but as someone who spent a big fraction of his career thinking about models for new physics at the LHC, I can tell you that 99% of proposals for new theories at the LHC are dead. So simply not being dead is better than nothing. Okay, so now there was a worldview, and now I'm coming to this sort of main challenge to this Ming Vase picture. There was a worldview that also emerged in the mid-2000s that strongly motivated this picture of at least for me, strongly motivated this picture of split SUSY, at least made it not crazy to contemplate. And that is this sort of orthogonal seeming picture of the world, where in fact there is maybe some underlying unique theory there, like string theory. The theory is unique, but it has gazillions of solutions at long distances, things that look like approximate vacuums at long distances. This doesn't bother us in the context of like the Schrodinger equation being unique and having you and me and elephants and tables and chairs as different solutions. But somehow there was this hope that when it comes for solutions that are vacuums of universes, that would be unique out of this unique underlying theory. And instead, there was this idea that no, it's not like that. The theory might be unique, but it has zillions and zillions of different solutions. Many of these solutions have a positive energy density for their vacuum. Those regions of space expand exponentially. And there's a whole cosmological picture I don't have time to go into that not only are all these different solutions there as approximate solutions of the theory, so-called metastable solutions, but that's also somewhere out there. If you zoom out and imagine a God's eye view of the entire universe, even outside our cosmological horizon, you'd see them all out there somewhere, realized. Okay? So there's, first of all, this gargantuan set of possibilities, maybe 10 to the 1,000 different possible worlds, maybe more. It's not so hard to imagine, by the way, how you could get such enormous numbers. All you need to imagine is that you have a few scalar particles, like the Higgs. Each one of them might have some potential that looks like that. Each one of them might have two different vacuums, so that doesn't bother you so much to have two different vacuums. But now if you have n of these particles, there's a choice of 2 for each one of them for where they could be, so there's all of a sudden 2 to the n different possible vacuums you could be in. You see, it's not hard to get exponentially large numbers out of a relatively smaller number of moving parts. That very roughly is the way all these solutions emerge in string theory. There are fields that correspond to the sizes and shapes of extra dimensions in string theory, and there's a reasonable number of them because you've got to get from 10 dimensions to 4 dimensions, and each one of them can have not maybe 2, but can have 10 or 20 possible places that they could lie. So you could have 50 or 60 particles with 50 or 60 places they could lie, and you soon put these things together at the same kind of exponentially large numbers. So there's exponentially many different possible vacuum energies, for example. And then the point would be that all realized out there somewhere, but almost everywhere in this multiverse, almost everywhere, for example, the universe is doubling in size so rapidly that all structure is ripped apart. No reasonable structure can ever form and be bound to itself gravitationally. So you might say that the theory is unique, but it has these gajillion different solutions. But if you look around in your mind's eye, this God's eye, you will look around, mostly it's lethal. There it's deadly, 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 deadly. And every now and then you find a few places where it's not expanding so rapidly that it rips structure apart. And that's the place you're going to find structure. And that's reasonably where we might be as well. Okay? So that's the picture of both the landscape of solutions as well as the idea that it's realized out there somewhere cosmologically. And I want to make 2 comments about this. One, an awful lot of nonsense is said about this whole story. Almost all the sort of popular discussion of it is about whether things are falsifiable, blah, blah, blah. And it's true that if you thought that the only way you're going to you're going to make predictions is to predict the value of the strength of the electric coupling or the ratio of the mass of the electron to the muon. In this picture of the world, those things are absolutely not predictable. They're not unique. There's 10 to the 1,000 different possibilities for them, okay? Now, many people take this as a giant disappointment. In fact, at some level, it's a much more extreme version of unification. It's an even more amazing version of unification, that not only the particles and forces in our vacuum, but in all these other different possible worlds are actually the same thing. They're different solutions of the same thing. And it's not like you have to take these guys and these guys and these guys and glue them in a giant Ming vase, but that already it's interesting that the same stuff that in one phase gives us our strong force and our electrons and all that stuff, in a different phase would give very different looking strong force and electrons and other things. Now, notice nowhere in this multiverse the apples fall up. Okay, apples fall down everywhere. The same basic laws. Things come together at 3 points in space-time, relativity, quantum mechanics. This is universal across this entire space of possibilities, but just the different possible elementary particles are the same stuff in different phases. So at an intellectual level, it's a more profound kind of unification even than you would have imagined with the Ming vase picture. But secondly, at a more practical level, people say, well, all the stuff is out there. Who knows if it's out there? It's outside our cosmological horizon. We can't even talk about it. Are we allowed to talk about it? We'll come back to that point in a moment. But I want to stress that part of this picture is in principle verifiable by experiments in one universe. Okay? Just to keep things simple, imagine it really was that you had thousands of scalar particles, thousands of scalar fields, and each one of them had a vacuum, had one of two vacuums. So there would be 2 to the 1,000 vacua. It is in principle possible. It could be very difficult, but it's in principle possible by particle physics experiments in this one universe to produce all of those 1,000 scalars, to verify that each one of them has a potential that looks like that. It's even possible in principle to make bubbles where inside the bubble, for some span, some distance in space, you're actually in the other vacua. Then you can imagine shooting particles into it to say, yes, the values of the couplings are different inside than outside, and so on. You could, in principle, do experiments to verify that part of the story. Okay, so it's conceivable that experiments could tell you, you know what? We have fields that allow 2 to the 1,000 different possible solutions. Okay, and if we saw that, you would immediately have to give up on the idea that even though the theory is unique, it could just be that theory with its couplings, and those 1,000 scalars and its very specific coupling. Even the theory could be unique at that level, and we would still not be able to predict, just from given the theory, we would still not be able to predict the mass of the electron or the ratio of the mass of the electron to muon and so on. Okay? So that part of the story, the fact that there is an exponentially large number of metastable states is in principle verifiable by doable experiments in one universe. In our universe, it's very likely to be extremely hard. You might have to do experiments up at the string scale or the gut scale or something to do that. But that part is not philosophy. That part is not metaphysics. It's just very hard physics. Very hard to do practical physics. The part of the story that is intensely confusing is whether we should think about all these things really out there in cosmology. Whether if we imagine zooming out in our mind's eye, really out there somewhere, all these different things are realized. And that runs into some really serious conceptual paradoxes that we don't know the answer to either way. The difficulty is that our universe is accelerating now. The fact that it's accelerating means that even if these regions are out there, light from them cannot make it to us. So we literally cannot see them. In a literal sense, can't see them. And so when we invoke their presence out there somehow as an explanation for why we found ourselves where we are, because there are all these possibilities are really there in space somewhere, but we live where we live because out there it's deadly, that we're invoking something in a region that we can't, in principle, at least naively, communicate with or get information from. That's something that's conceptually interesting and has led to all kinds of paradoxes to try to sharpen and understand better. Doesn't mean we know the answer. We don't know that it does make sense. We don't know that it doesn't make sense. But to the extent that there is something conceptually confusing and strange, that's where it is. Okay, so anyway, this is the quick summary of the landscape picture. But I want to stress that again, in a sense, it's an even more extreme kind of unification. But this Ming-Vase kind of unification hope is really naively dead here, okay? All right. So let's move on to the other, to the more conceptual kinds of unification. So first I want to tell you about why reductionism is probably wrong, and that we have evidence for some kind of link between very high energies and very long distances. The first indication is that if we imagine doing accelerator experiments at higher and higher energies, we normally think we probe shorter and shorter distances, but at some point when the energies become incredibly large compared to the Planck scale, again, we put so much energy into the region that we're looking at that we make a black hole. And as we make the energy much, much bigger than the Planckian energy, we make the black hole much larger than the Planck length. So that's the most naive first indication that very high energies no longer probe very short distances. They start probing longer and longer distances again. Okay, so that's something we can predict about the real world. Ultra, super, duper, duper high energy scattering is something where roughly we know what happens. We make very large black holes. Very large black holes evaporate by Hawking radiation. Okay? So in a sense, now we don't know the fine details of how the particles come out, but we roughly know what happens. You make big black holes and they evaporate by Hawking radiation. And the fact that we know very heavy objects or very large black holes has all kinds of qualitative consequences on the structure of physics at all distance scales, including at low energies. For example, black holes evaporate by Hawking radiation. For consistency, they need to have an entropy. In a sense, they're the most entropic objects the universe can possibly have. But the number of degrees of freedom in any region of space, which you would naively think scales like the exponential of the volume of the region of space, because we know the entropy of the black hole is actually proportional to its area, the maximum number of degrees of freedom that you can have actually has to scale not like e to the volume, but e to the area. Okay? By the way, sometimes people mistakenly say that this is something that's utterly shocking to a long-distance physicist. It's actually not utterly shocking. And in fact, any surprise is in the opposite direction. If you take a big ball of gas, like a star, and you just make it more and more massive until the point that it will collapse to a black hole, right at the point where it collapses to a black hole, the amount of entropy that it has is nowhere near the entropy that it will eventually have as a black hole. Vastly smaller than the entropy that it would have. In fact, it's roughly e to the area over g Newton to the 3/4 power. Okay, so in fact, black holes have even more entropy. They have even more degrees of freedom, which sort of makes sense, right? Everything is getting crushed gravitationally, and then all the other degrees of freedom that are there are sort of getting inevitably excited when this very singular thing forms. There's no blatant contradiction with any obvious fact, but it reflects the fact that gravity is a long-range force. And so I can't just keep piling things into a region and turn on more and more and more degrees of freedom without inevitably having to have so much mass that it collapses the region into a black hole. It does mean that it's very unlikely to be true that there's some picture of the world with some kind of microscopic degrees of freedom, anything like a lattice or any kind of condensed matter system of any sort in our universe, which at long distances gives rise to something that looks like us. There's many reasons that can't be the case, but this idea that gravity is not really local, that its degrees of freedom don't grow with the volume, but they grow with the area, is a qualitative one people have known about for a long time, and it's a reflection of this UVIR correspondence. Okay, now in the past 10 or 15 years, there have been some indications that there are other consequences of this. So what I told you is that there's something amazing that we know about very high energy objects are big black holes that are big, so they go back out to long distances. So that's some indication that there's some impact on very low energy physics of the consistency of very high energy things like black holes, and that's in a sense one of the topics of this workshop here was about that kind of a connection. And one simple example of this kind of perhaps surprising consistency condition on very low energy physics, following loosely in some way from the consistency of the physics of black holes, is the following observation. In the real world, we know that gravity is much, much weaker than all the other forces. So the gravitational force attraction between two electrons is 42 orders of magnitude weaker than the electric repulsion between them. But as a theoretical physicist, in your mind's eye, you could imagine making forces weaker if you wanted. There's a parameter in the theory. You could just dial the coupling, make it smaller and smaller and smaller and smaller. There doesn't seem to be anything wrong on the face of it with making the couplings arbitrarily weak. And yet, there's many indications that something should eventually not let that happen. For example, there's always black holes that have both mass and charge. And if you take black holes with the sort of largest charge that they can have, so there's such a thing as an extremal black hole whose mass is exactly equal to whose mass in Planck units is exactly equal to its charge. You can't make its mass smaller than that and have a sensible solution in general relativity. So that object is one for which the gravitational force exactly balances the electric force between them. And so there are large objects out there, these black holes, whose mass to charge ratio is equal to 1, at least in Planck units. So this conjecture says that there should always be some elementary particle out there whose mass to charge ratio is smaller than 1, smaller than this one that's associated with the extremal black holes, because that would allow these charged black holes to evaporate into their constituents, which are these the kind of elementary particles that they're made of. At least that was a heuristic motivation for this. And it makes various more technical predictions that you can go and check in many examples and study in more detail. And it seems to be true so far. But what I want to suggest is that, or what I want to say is that, so this is an example of something that seems naively consistent to a long-distance person that deeper gravitational arguments seem to prohibit. And it's another example of a sort of deep unification. If this conjecture is right, it means that if you have gravity and other interactions, you can't treat them separately. You can't say there's gravity and there's something else, right? There can't be some sort of cookie-cutter picture of the world where you combine things willy-nilly any way you like. There has to be something that knows that you can't make that force arbitrarily weak, weaker than a certain specific amount relative to a gravity. Okay, so we can't treat gravity and other forces in isolation. Okay, there are other more qualitative indications for this UVIR correspondence. One that we know essentially nothing about, we know essentially nothing about in detail now, but is fascinating and we'll hopefully know more about in the future, is the following. I'll focus on this aspect of the problem. You know the universe is expanding, right? So somehow, as the universe is expanding, if we look at all the sort of degrees of freedom that make sense, at any moment in time, this notion that space-time breaks down and so on makes you think that you can make sense of things up to the Planck length. Fine. So there's something as funny as going on at short scales. But the universe is getting bigger and bigger all the time. So the number of degrees of freedom we have access to is growing as the universe grows. Somehow, degrees of freedom are born in an expanding universe. See, if you imagine putting things on sort of a lattice or some kind of crystal or something, then what would happen as the thing expanded? Well, everything would expand. Also, the lattice spacing expand. Everything would expand. And that's not what we see. Okay, what we see is somehow degrees of freedom are constantly born. They come from somewhere as the universe expands. Where do they come from? We don't know. Okay, we don't know precisely where they come from. Somehow there are degrees of freedom sitting there that we do not interpret as degrees of freedom that live and move around in space-time, but that which are born in an expanding universe. So that's one thing right there, that what we call very long-distance degrees of freedom today were born as super-duper trans-Planckian high-energy degrees of freedom early in the history of the universe. Where do they come from? So that's remarkable. The long-distance degrees of freedom today were super short-distance high-energy degrees of freedom early in the history of the universe. And this keeps going. There's something I find really amusing, is that if you look at the whole history of the universe, at least the way we might expect it, or at least we think in many nice pictures for cosmology. There's some kind of Big Bang singularity. There's a period of accelerated expansion as in inflation. There's this intermediate epoch where you have radiation and matter and structure forms and all the rest of this stuff happens. Now we're starting to accelerate again today. And in any of these landscapey pictures, the most likely future fate of our universe is that we will decay out of our metastable vacuum into one of these lethal places in our neighborhood where the energy is much, much lower. And when we go there, it turns out inside there, the universe undergoes a big crunch. Okay? So for any observer, any typical observer living through this whole cosmological history, there's an incredible symmetry between the beginning. The whole picture is almost sort of time symmetric, right? You go singularity, acceleration, excitement, life, love, etc. Acceleration, death, and a singularity again, right? So these, in other words, these degrees of freedom that started off life as ultraviolet, became infrared, will become ultraviolet again at the end. Okay? And we don't understand any of how this happens, but it's another kind of deep unification between long and short distances. Somehow the long and short degrees of freedom are the same. And this is true because of gravity and cosmology and quantum mechanics. It is not true of phonons in a solid. Those degrees of freedom are not, they're not the same as the underlying, they're collective modes of the underlying atoms and molecules, but there's no sense in which phonons are atoms and molecules, right? They're an approximate description at long distances. This is very different in our universe that has gravity and quantum mechanics, relativity. It's something different. Okay, so let's now talk about the gauge gravity unification. So this is something that actually that begins with what might look like the very earliest hint for it is what might look like a dumb thought you could have as a sophomore in college or something. You might think, people tell you the photons are spin 1 particles, they're Yang-Mills theories, but photons are massless spin 1 particles or gluons, spin 1, helicity 1. A graviton is a spin 2. So why can't the graviton just be 2 photons on top of each other? Okay, so this is a great theory, right? So after all, if I take 2 photons going this way, then they look an awful lot like they have the same spin. It's the massless particle moving this way, and it has angular momentum too. So this makes you think that somehow gravity should be like 2 copies of a photon. And of course, literally that theory is ridiculous because there's no force that's keeping the 2 photons next to each other all the time. And if you beamed your laser beams a little bit sideways, it would no longer look like a graviton. Okay? But nonetheless, there is something to this idea. In string theory, for example, this is exactly, there's something very much like this, because gluons, photons and gluons are associated with little loops of open string, whereas particles like gravitons are loops of closed string, and there's really a precise sense in which a closed string is like 2 open strings glued together. Okay, so both at the level of just looking at the spin of these particles, closed is open squared, gluon squared is graviton, closed strings are open string squared, gravity is like Yang-Mills squared. Okay, so at this very cartoon level. And in fact, in the last 10 years or so, and actually goes back to work done by, it had its origin in work done by string theorists 30 years ago, but has been since understood as a very general property just of gravity and Yang-Mills theories in any number of dimensions. Has nothing to do with any details of any extra details. But it's an example of a hidden kind of remarkable relationship between different theories. If you look at the scattering processes involving gravitons, there's a very precise sense in which the scattering process involving gravitons can be computed instead by scattering involving gluons and squaring them. And it's not exactly squaring. You have to interpret the squaring a little bit. There's a little bit of a dictionary to mean exactly what you mean by squaring, but it's still an utterly amazing fact that's totally unobvious. Okay? If you stare at the Lagrangian for general relativity, it's some horrible, complicated, terrible mess. Even this Lagrangian for Yang-Mills doesn't look so great. Even calculating these amplitudes by hand using the textbook rules is impossibly complicated. You would certainly never guess just staring at that there's any such relation at all, and yet there is such a relation. So that's an example of a hidden unity, right? There is no reason these things had to be the case, and yet there is some very precise sense in which gravity, even these interactions that seem very different, they're described by different Lagrangians, different seeming set of ideas, actually have this deep connection. So this is a hidden unity that Lane discovered for decades, but is lying there right under our noses. Okay. So this relation that closed is open squared, that was the first, so again, it starts with this dumbest observation about the spin. Then in string theory, it gets more concrete. The closed is open squared. Now, even for just gluons and gravitons, no strings, nothing like that, we have the kind of relationship that I told you about. But now we're going to talk about the gauge-gravity duality. And here I'm going to back up by reminding you of some big lessons from quantum mechanics, because in a sense, we're going to follow these lessons from quantum mechanics to their bitter end and be led to thinking about these holographic correspondences between different sorts of theories. So here are two of the big lessons from quantum mechanics. First is it's important to pay careful attention to what precise observables are. Okay, so so even though in the classical world we can approximately talk about position and momentum, it's really important, even though it's practically irrelevant for many questions, that in quantum mechanics we can't precisely know what the position is if we know what the momentum is, and vice versa. So the word becomes or and not and. Okay, so it's position or momentum, not position and momentum. And secondly, another lesson that we normally don't emphasize, but has always really struck me, is that there were classical physicists who were tremendously disappointed by quantum mechanics. They couldn't, of course, disagree that it worked, but there are people who thought, there's this Laplacian dream about predicting the future. You give me everything now, I can predict everything about the future. Quantum mechanics represented a drastic, massive reduction from that point of view in the power of physics, right? You couldn't predict anything about the future with certainty anymore. Okay, so other than probabilities, but an infinite number of things that we could talk about before we could no longer talk about. So quantum mechanics implies a drastic loss in the number of meaningful observables. On the one hand, things that we can precisely talk about, the drastic loss in these precise observables. But there is a silver lining, and the silver lining is that if there is many fewer things to talk about, the things that are left have to be related to each other in some subtle way that you missed before. You missed before because you thought they were different and you could talk about different things. There are fewer different things you can talk about. Therefore, the things that are left have to be more closely related to each other than you realized before. So for instance, we lost determinism, but we gained that precisely because of the loss of determinism, we gained that particles and waves can be the same thing. Okay? All right. So we're gonna follow that logic. So first, let's remind ourselves of what quantum mechanics says we're allowed to talk about. In quantum mechanics, in order to talk about any exact observable, we have to do two things. Because the theory is probabilistic, we have to make infinitely many measurements in order to extract the probabilities with infinite accuracy. I want to talk about something precisely. So that's one infinity. The second infinity is we have to do the experiment with an infinitely large measuring apparatus. And the reason is that any finite measuring apparatus itself has quantum mechanical fluctuations. And so there's a systematic uncertainty to any observable associated with it. Okay? So, for instance, if I'm made out of roughly 10 to the 30 particles. If I try to measure anything, the G-2 of the electron, anything, it doesn't matter. If I try to measure anything to 10 to the power of 10 to the 40 decimal places, so that's very ridiculous, okay? But if I try to measure anything to 10 to the 40 decimal places, there's a problem. Because by the time I get to the 10 to the 10 to the 31st decimal place, 10 to the 10 to the 30th decimal place, maybe I was supposed to write down 7, but me as a quantum system made of 10 to the 30 things, I could have a quantum mechanical fluctuation, I could write down 2 instead. That's one of the more mild things that could happen. Worse, I could tunnel out of the room. I'm not in the room anymore. I turn into a cloud of dust. there's all kinds of things that obstruct me as a finite being knowing anything to accuracy better than 10 to the 10 to the 30. Now, it's ridiculous, which is why we don't think about it. The first infinity with doing the experiment over and over again, there the error is 1 over root n. And so experimentalists care about it. It's called statistical error. And we care about it. The other one goes like e to the n, where n is the number of things you're made of, and so we don't practically care about it. But those are the 2 infinities that are needed, conceptually, to talk about precise observables in quantum mechanics. So quantum mechanics asks you to do this funny thing. You have to drag these infinitely large apparatuses with you everywhere around you go. And it's the correlations between the finite systems and these infinite apparatuses that are given meaning in quantum mechanics. Okay? Now, in a world without, it might be funny, and you might like it, not like it, but it's true. And that's why, in the absence of gravity, in the absence of cosmology, there's nothing funny or weird going on. But, you see, gravity doesn't like this. Gravity does not like this division of the world into 2 pieces. The piece that's looking and the piece that's being looked at, because everything gravitates universally. And if you try to do an experiment in this room, some fixed size room, you try to measure anything to infinite accuracy in this room, you can't do it. Because you'll have to make your apparatus bigger and bigger. But if you make it bigger and bigger, it'll get heavier and heavier. And before it gets arbitrarily heavy, it'll get so heavy that it'll collapse the whole room into a black hole. Okay? And then you can only do the experiment a finite number of times before you get killed at the singularity. And so there's nothing in this room that can yield a precise observable. This is amazing. Okay? It's a very simple but deep fact. It was understood by people already in the 60s that there are no local observables. So we went from classical to quantum. The world isn't deterministic. That sucked. Okay, it's probabilistic. Okay, fine. But we have all these probabilistic things we can measure. And now further, we add gravity. Nothing you can do in a fixed size room even makes sense quantum mechanically. So there are no local observables. We lose even more. Gravity and quantum mechanics, we lose even more. So what can we talk about? Well, we have to talk about something which can be measured by these infinitely many apparatuses, infinitely large apparatuses. All you can do is push these apparatuses out to infinity. So they become infinitely large, but infinitely far away from other things. And they can shoot particles into the interior of the space-time. The particles can bang into each other, and they can go back out where they're measured by things at infinity again. Okay, so this is the only kind of observable that we have left when we have gravity and quantum mechanics. The observables live at infinity. Okay? And this was, as I said, appreciated by people like Bryce DeWitt already in the 1960s. Okay? Now, in our space-time is, to a decent approximation, flat space. Of course, it's ultimately cosmological, but to a decent approximation, it's flat space. And these experiments have the additional advantage of being what we actually do, what our experimental friends actually do. We're very close to these experiments, right? These are scattering processes where you send things from infinity, which is the same as 27 kilometers around ring at the LHC, and they go into a small distance and they come back out to infinity, because 27 kilometers is pretty infinite relative to the size of the protons that you're colliding. Okay, so these experiments are the conceptually deep, correct observables when you have gravity and quantum mechanics in flat space. They also happen to be very close to what we do in real experiments, which is why we care about them for many reasons. So those are normal scattering processes in flat space. But this general ideology, though, tells you that the only things that make sense when you have quantum mechanics and gravity, you have to go find some boundary somewhere infinitely far away where you can do the measurements and get exact quantum mechanical results. And 20 years ago, string theorists found an incredible model of the world in a box that, physicists love to put things in boxes. And it's very hard to put something gravitational and quantum mechanical in a box because everything is fluctuating. But they found this world in a tin can, which is, for which this whole ideology can be made very, very precise. So this is this famous picture of the inside of a tin can. Inside the tin can, though, the space is warped, it's negatively curved, it's anti-de Sitter space on the inside, and it's like a tin can in the sense that, on the one hand, if you're inside, the warping of the space means that the distance to get out to the boundary is actually infinite, and so that's good. That's what allows the apparatus to get arbitrarily far apart from each other, arbitrarily big, to have all these observables make sense. But on the other hand, light takes a finite amount of time to go from the center and bounce off and come back. So in a very sort of meaningful sense, it's like the inside of a tin can. And so if you now take this point of view seriously, the only observables can only be measured out on the walls of the box, then it's a natural question to ask, why do I need the inside at all, right? The inside is something that I'm using in my head as a theoretical physicist to try to make sense of the observations that took place from, I can ping the box on the outside and send excitations in and have them come out, but I'm not living inside. The only observations I make start and end on the boundaries of the box. So could it be there's a theory that just lives on the walls of the box that actually gives me the same result as everything that I imagine associated with gravity and strings and everything else like that in the middle? And the answer is amazingly yes. So this is a kind of astonishing sort of hidden unity, as far away, in some ways, quite far from that Ming Vase picture. That Ming Vase picture wanted us to think that the gravity forces in the Standard Model, the force of the Standard Model and gravity and everything were sort of unified into this one string. Okay, this is something more radical, more strange, more unexpected, that the gauge forces of the Standard Model could be gravity in disguise, right? Not that you put them together, but that there are different sides of the same coin. Okay? Of course, here it's not gravity in our space-time, but gravity in but gravity in this universe with one extra dimension and this tin can. The inside of the tin can, not just the walls. Okay, but this is an instantiation of this general philosophy. It's sort of forced on us by taking what we can observe in quantum mechanics seriously when we also have gravity, tells us we can go out to the walls, and therefore that's all we can do. On the walls, there's a theory that can live on the walls, and that theory is just a good old-fashioned theory of particles. But the interaction between the particles is so strong that the particles are created and destroyed in such abundance that it's not useful to follow them individually. The collective modes of the interaction of these strong interactions of these particles is equivalently describes the inside of this tin can in one higher dimension. Okay, oops. All right, well, this was upside down. But anyway. Let me say in words, you can't see this. I want to say that, this has been a huge topic of work for 20 years. It'll go on for more decades still. But I want to point out a kind of a huge tension, at least to my mind, a huge tension between this picture and another picture that we learned slightly earlier in the 90s. So string theorists taught us two things in the 90s. One of them is that there's one master string theory. They're all unified together. There's one giant animal, and that has all these different solutions, and they're all connected to each other. And maybe there's even this gargantuan landscape that connects even more things, metastable solutions, and so on. But there's a sort of big, giant unity, one huge object that sort of unifies all of them. That's one picture. Another picture is that any quantum mechanical theory, and in this picture of the gauge-gravity connection, ultimately it's really any quantum mechanical theory can be, on a boundary, can be thought of as describing some theory of gravity in a bulk of one higher dimension in this sort of holographic way. So one picture is ultra unified, right? One picture, so there's this one master thing and we have all these different solutions. The other one is ultra ununified. It says that every quantum mechanical theory is privately defines its own theory of gravity. And on the face of it, I could talk about each one of them individually, and nothing in our current language tells us how to group together the space of all quantum mechanical theories together somehow, okay? In other words, if you only knew the second point of view, if you only knew the second point of view between quantum mechanical theories and gravitational theories in ADS spaces, I think it would be a big shock to you if someone told you there is a master theory in the interior and all these different things that you're talking about are actually different phases of that one theory. I don't see any reason why that would be expected. So there's some tension between these two points of view, and this is a big speculation. I think it's a speculation a lot of people make, is that there's probably some, in this point of view that's been developed for 20 years, the theory on the boundary is king. This quantum mechanical theory is king, and the kind of space-time description, or the space description, the time is not coming along for the ride. The time that flows on the boundary is the same as the time in the interior. That's very important. But the space kind of comes out as some approximation to the quantum dynamics of this theory. It's conceivable that there is a counterpart to this description that we don't have yet, where here quantum mechanics is king and sort of space is approximate and comes out. And perhaps there's some complementary description to this where the picture of the space on the inside is somehow more obvious, but then likely quantum mechanics will be less obvious in this picture in some hard to define way. But this is a motivation to try to find a way of talking about physics in a way where we're not so slavishly adherent, at least to the grammar and the words that we associate with standard quantum mechanics. Even if we're doing standard quantum mechanics in the end, that it could be that there is some way of talking about the physics in the interior that's more unified, more space-time centered, less manifestly quantum mechanical. This is a wild speculation. It's a speculation that a number of people make from time to time, and I think that it's something that we're going to see more of, and will be made more concrete as time goes on. But I'm out of time, but I want to say what the real difficulty is. The real conceptual difficulties that we have to face are that we know how to put the world in a tin can. Our world is not a tin can. Okay? And our world isn't even flat space. Our world is cosmological. And this is the biggest set of problems, I think, and I think many people think we have to confront in physics. It's not clear we're going to confront them this decade, in 50 years. It's not clear when we'll make real progress on them. But our universe is not the inside of a tin can. Not only did it likely emerge from this singularity in the deep past, or the Big Bang singularity, but also it's accelerating today. And that acceleration has huge ramifications. For one thing, we only have access to a finite number of degrees of freedom. There are the regions in the universe that are very far away. No information from them will ever make it to us. What we see out there in the universe today is what we're ever going to see. And that means that for the first time, there's a fundamental finiteness that's shoved on top of our heads. Okay? We cannot make apparatuses arbitrarily big. We can make them enormously big, but we cannot make them arbitrarily big. The whole picture of quantum mechanics, of dividing the world into this infinite measuring apparatus and the finite part being looked at, is not even... There's nowhere we can go. There isn't even a boundary we can in principle go to where we can do that. This fundamental finiteness means that there's something flawed with that entire paradigm. Okay? This is what I was referring to in the very beginning when I said that we might need some extension of quantum mechanics. Now, not saying quantum mechanics is wrong, but this is a situation where quantum mechanics just doesn't know what to do, right? We can't make things infinitely big, so there are no perfectly precise observables of any sort that we can speak of, and that's something that's forced on us by the accelerating universe. So, and of course, the other important thing in cosmology is time. You know, whatever happened, what happened near the Big Bang is very likely the notion of time began near the Big Bang. So we can't just leave time alone. We can't just talk about emergent space, which we're learning how to do very well in this world in a tin can holographic picture, but also emergent space and time. And these are the really outstanding challenges for the next decades. All right, so with that, I'm really out of time, so I can't talk about the much more speculative things. That's maybe a good thing. I will leave them up here in the slides if anyone wants to look at them. But actually, maybe I will just, that this is the most speculative thing of all, but since I was just talking about it, maybe I'll just say 30 seconds about it, because it just piggybacks on what I was just saying. As I said a number of times, quantum mechanics forces us to split the world into two parts: infinite observers and finite systems. And we've already seen gravity doesn't like this. Cosmology really doesn't like this. And I actually emphasized a moment ago this one feature that there are no precise observables in when we have the accelerating universe. Something that I find really also disturbing. You see, this is a very, very esoteric thing. This is a very, very esoteric thing because it means I just told you that I'm made out of 10 to the 30 things, so I can't talk about anything with precision 10 to the minus 10 to the 30. This just extends that to the whole universe. The whole universe doesn't have more than 10 to the 10 to the 120 degrees of freedom, so nothing makes sense to accuracy better than 10 to the minus 10 to the 120. Okay, so you could really not give a crap about this, okay? If you didn't care about you yourself, you care even less about the whole universe. This is another issue, though, where the very similar things come up and where it matters more. For instance, how many of you have thought that, one of our big challenges is to understand what happened at the Big Bang, okay? So you might think that, what's happened at the Big Bang might have some imprint on things that we could in principle measure. There might be very tiny effects, but they might have some imprint on things that we could actually measure. And if you really imagine doing cosmology, you'd have to put some boundary condition at this singularity moment to be able to calculate anything. And you might imagine that the answers for cosmological correlations that you might measure at late times would depend in some way on the choices you made there. So different theories for what happened there, different choices would lead to differences that you can in principle observe. Okay? So there might be really tiny effects, but you might in principle be able to observe them. And that would be true if our universe was not accelerating. Okay? But because our universe is accelerating, because of everything that I told you, because of this finiteness, there is a resolution to there is a limit to how much we can learn about very heavy physics or very early physics near the Big Bang singularity. And in fact, if you believe in inflation, never mind getting back to the Big Bang, you can ask, let's say there are particles. Let's say there was something stringy going on in inflation. So there are particles, maybe stringy particles are 100 times heavier than the scale, the size scale of the universe during inflation. Their presence or absence would give rise to exponentially small corrections to the correlation functions that we could measure. And you might imagine it's important. There are some consistency conditions on them. They're very small, but they matter. There's some consistency conditions on them. You could in principle measure them. And you could in principle measure them if the universe got big enough that you could get a large enough statistical sample of different regions of the universe to be able to make these statistical measurements to that accuracy. But because of the accelerating universe and this finiteness that we're talking about, there's a limit. And that limit is much more practical than this 10 to the 10 to the 120 that we're talking about. In fact, particles that are just 50 times heavier than Hubble during inflation, we can't even in principle learn about their presence by any experiments we can do in our universe. Never mind what happens at the Big Bang singularity, okay? So all of that stuff, in other words, it's not just, it's hard. The fact that the universe is not infinitely large, we don't get an infinite number of different regions of space, so we can't make we don't get a large enough statistical sample to be able to make these measurements sufficient accuracy, means that all of these exponentially tiny effects associated either with the Big Bang singularity or with heavy enough particles are washed out by quantum mechanics in the late universe, what's called cosmic variance, the fact that we don't have a finite number of samples that we can check. This cosmic variance wipes out any information about very heavy physics, even just 50 times heavier than Hubble during inflation. Never mind what's going on near the Big Bang singularity. This really bothers me. This means that, again, if you take the standard things that we're allowed to talk about in quantum mechanics seriously, it's not even meaningful to ask what happened to the Big Bang. It's a content-free question. It's like asking about the position and momentum of a particle at the same time. This really bothers me. I think this is one of many indications that there is that either we have to live with this, but this is you see, the reduction, now we're taking this really seriously. We have fewer and fewer observables, but now we've finally reached a point where we appear to have no observables at all. And I think the only thing that's left, the only bit of unification that's left that could take care of this is removing this artificial distinction between the system and the observer, this cut between the infinite system and the finite observer. This is incredibly speculative. I have no idea how it will actually eventually happen, but I think if you take this logic to its bitter end, this is where it's pointing to. And I'll just make this last comment before ending. If you think there is something to this, that somehow there is a fundamentally finite system, not infinite. There's a fundamentally finite system, and this finite system gets an interpretation in terms of large observers observing small systems. So there's a way of slicing this finite system up approximately into observers and systems. Then there's at least a vague possibility. There's a vague possibility that while there's something correct about this landscape of solutions in string theory, they all, in some sense, exist as metastable solutions. It may be incorrect to think about them at all as literally realized out there somewhere in space in a literal sense. And they might be more akin to different ways of slicing up the same large animal into approximately into observers and systems. So that's very vague, very speculative, but it's something that that at least gives you a picture for how the part of the landscape which does something useful for you to even make it possible to find from this one underlying theory universes that look like ours, that part could be true while not foisting on you this ocean of conceptual paradoxes associated with precisely how they're realized out there cosmologically. All right, so that's it. We're going to forget about experiments altogether. But I hope you did get a sense that we're asking quite profound and deep questions in this subject right now. I do think this was alluded to in my kind introduction, but I strongly believe that it's a singular time in the development of the subject because the questions are really deep ones. We're not asking about the details of this or that particle or this or that specific phenomenon. We've understood largely many of those things from general principles, even quite remarkably. But we have these more structural questions about the underpinnings of space-time, the origins and fate of the macroscopic universe. And to me, there are increasingly deep and unexpected notions of unification, far beyond the Ming Vase picture, far deeper, more unexpected, more surprising, some disquieting, some welcome, some hated, but all carrying this idea of unification beyond what we imagined 30 or 40 years ago. And all I can say about it for myself is that it's clear any human prejudice we have ahead of time for what the answer looks like is just going to be a hindrance to progress. We should just study the things that are deeply tied to these general principles and follow them. Not have a demand ahead of time what the answer should look like, but follow them where they lead us. And more and more of these things are being uncovered in our theoretical exploration of field theory and string theory. I didn't have any chance to say it, but we definitely need more input from experiments from the LHC, continuing cosmological observations, a whole new frontier of small-scale experiments, but in a colloquium twice as long, I would talk more about these things. But I do think it's an exhilarating time to be doing physics. I just wish I was 20 years younger, because I don't know if real progress on these things final level progress even on parts of these problems will happen in 10 years, but they might happen in 20 or 30, and I would rather be 20 or 30 years younger so that I would live to see the end of some of it. But anyway, it's really a perfect time to be 25 years old. So thanks a lot.
Okay, thank you, Nima. So Nima's talk is over, but the real challenge starts now. We have to take him to the airport on time.
Yes.
So I will allow only one or two very quick questions.
Hi, so my question has to do with this thing that you were emphasizing a lot on, the fact that the requirement to measure something with infinite amount of precision.
Yes.
But why do you exactly want it? I mean, why aren't you happy with, let's say, 13 or 14 decimal places? And also, does this have something to do with the fact that space-time is quantized, or if it is not quantized and it's continuous, then you don't even have a problem of creating more stuff? Because, I mean, if you think of like all the... Okay,
I got the question. So let me say the first part. It's a fact about the history of physics that it's been very useful to think about what the precise observables are, because the precise observables are what some mathematical theory for the world should be about. Okay, Exactly what you said, you could also say about classical physics. Who cares that you don't know position and momentum? Who cares about the uncertainty principle? To much better accuracy than 14 decimal places. For you and me and baseballs and soccer balls and so on, we know the positions and momenta of particles at the same time. But it's important conceptually to know the things that have precise meaning, because that's what a theory should be about. That's what a precise mathematical theory should be about. Now, you might say, maybe for the first time we no longer care about precise mathematical theories. Maybe. But this is taking the 400 years of the logical development of the subject seriously. So that's the answer to your first question. That's why we care about the precise observables, because things that are not precisely observed probably are not part of the underlying equations. And we saw that already most dramatically in the transition from classical to a quantum. For the second question, one of the remarkable things is that we know for almost, I alluded to it already, we know for almost sure that this picture of a quantization of space is wrong. It can't be that what's going on is like, atoms of space and time, where you go down, the surface of the table looks smooth, but then you see it's made out of molecules and atoms. That cannot be what's going on with the space-time, because any such picture of any discrete structure would break Lorentz invariance. It chooses a frame. The table chooses a frame, okay? The vacuum of space-time does not choose a frame. Or said another way, those atoms, the discrete structure better be small, but in whose reference frame are they small? Okay? So if it was something like atoms of space-time, the subject would be vastly less interesting, because then, okay, something like that's going on, and until you got to very high energies to see what that lattice looked like, you could imagine a million different ways it could look, and it wouldn't be too interesting to try to speculate about what it looks like. But it's this existence of Lorentz invariance that makes a humongous difference. Okay? So Lorentz invariance kills immediately many of these naive ideas about space-time, about quantization of space-time. But even putting that aside, if it was like a little lattice and the universe was expanding, then it's not like it's like you're stretching it out. In that picture, what would be happening, even if you ignore this thing about Lorentz invariance, it's like as you stretch out, then all of a sudden some new atom is born that wasn't there before. You stretch out, some new atom is born, some new atom is born. Classically, the expanding universe, you really think of as more space being created all the time. And if there is this sort of quantization that you're talking about, then as you double it, then poof, another site has got to appear in the middle, another one's got to appear in the middle, and so on. And so they're sort of coming out of somewhere, okay? And we don't know where they're coming from. But
okay,
as I said, the remarkable thing is that these very long distance things come from very short distance things and eventually go back to being very short distance things again. Yeah.
So unfortunate as it is, I'm cutting it down now.
Okay.
So at this point, let's thank Nima for this beautiful talk. Okay.